Just okay. Let's get cracking. Let me do a full screen. As usual, if you guys have questions, feel free to put them on the chat. I will be able to see them, or just sort it out. I don't mind being disturbed in the middle. So today I thought, because this is the last class, and what we have touched upon deep learning is only like really the building blocks, the basics, right? Like most of the real world applications are far too nuanced and advanced. So I thought, instead, and of course there's no way for us to like cover any of these things in so much detail, but at least I thought, let me give you a hint of what like the advanced topics, or like the cutting edge research type topics looks like, right? And some of these things are like they are not very new, in the sense these are the problems people have tackled since the advent of machine learning, or advent of deep learning. And some of them are like very new, and some of them are more application focused. And I intentionally chose this wide mix of topics because these are the things that will continue to be in the conversation of deep learning. There's some people who are afraid to use deep learning, and for good reasons. And some people are like, oh, what is the use case? Because sometimes the non-traditional things where you would not think a machine learning could be used, like image compression, even there it's used. And and things like cancer diagnosis, where we would be like, how is deep learning or CNNs used for cancer diagnosis? In the end, the actual configuration isn't very different from the ResNet and other stuff, but there are other things that you have to worry. These are the things I will show you today. And in all of these areas I have personally worked, or I have published papers. So if you have any curiosity to understand, curiosity to know more, feel free to reach out to me, and I will share you the actual papers that I wrote on these topics. Now, one thing which you guys have, I'm sure, already noticed by now, right, that the number of parameters that these networks have or take, of course they can work with fewer parameters, but turns out that as you add more parameters, they become better, and people started just adding more and more and more parameters. So at some point, we have to always ask the question, right? That is, surely there must be some trade-off, right? What is the downside of having more parameters? So now, one of the downside is that these things need very expensive compute, very expensive GPUs. Like, for example, the GPT-3 model that, and there's only 3 companies in the world that can, even afford, or even, be in a place to train such a thing, right? Like, it is out of touch for common people like you and I. So there is a downside of these things. So obviously, you know, we looked at these kind of neural networks. So in theory, this is what people think neural network deep learning is, but in practice, it's like this, like many layers. In fact, if you see EfficientNet and other stuff, it is even like 10x more than this. So and the downside is it is not for everybody now, right? Because now it gets secluded. Now only people who have the money, who have the leg up, can use it, and that's not good for any technology. So and what we saw in over the years is the number of parameters just kept blowing up, and people stopped making smaller models because everybody only cared about accuracy, and obviously accuracy is important, right? And because if your model is not accurate, you will not use it, even if you can afford to use it. But in the last couple of years, people have started thinking about efficiency. And so in this particular plot, which is already a few years old, and I think if somebody were to make a newer version of this plot, these circles would be as big as the whole graph itself. So now, at least one thing which happened is, very early on, people, when they were making VGG, they realized you don't need these many parameters. So people started, making networks with, fewer parameters. But you should not get fooled by fewer parameters. Just because ResNet has less parameter than VGG doesn't mean that ResNet is cheaper to run. Of course, depends on what ResNet. Like ResNet 101 definitely will take more, power or more compute, because it has, or will take more time, because there's no time here, right? Because if you have 20 layers of 100,000 parameters, Or if you have 5 layers of 100,000 parameters, 5 layers is going to finish compute much earlier, right? So the inference is taking longer and longer. And for real practical purposes, you never want to wait, right? So if you say, hey, Google, and if Google takes, 30 seconds to wake up, or by the way, my phone just woke up. So if Google takes 30 seconds to wake up, you would be pissed. So you want these things to really be, on demand. It means it has to be very fast at doing inference. But if you have more parameters, more layers, it's not going to be. So as you can see, there's this, like dichotomy that has to be fixed. So obviously one idea is, do we really need all these layers? Do we really need all these parameters? Can we simply, prune them? Can we simply make them lean? And you can just think of it as like, after the model is trained and built, like some ninja comes and just chops off parts of the network. Now, question is, of course, you will have to pay some penalty of having, by removing some parameters. But what is the penalty? Like, how much does the performance deteriorate? So there is a whole line of work, and every year there's tons of paper published in this area of reducing the parameter size, of pruning of deep networks. And I also have a paper in that. And you'll see there's like plenty of work. And one thing which is very interesting in this is, if you take a network that has, say, 100 million parameters, and if you prune it down to 50 million parameters, it still has relatively good performance. So in this plot, at the very top left is your original network. And as you start reducing the number of parameters, after, remember, this is after the network is trained. So first you train with all the parameters, and then after it is trained, you prune them, you remove them. And I'll show you what's the idea, how to remove them. But if you remove them, of course, there are like many different techniques of removing them. All of the techniques have their own trade-offs. But if you use the best technique, like for example, this one, called as Taylor series, you can see if you remove 20% of the parameters, it hardly changes in performance, right? Only when you reduce like 80% of the parameters, then the performance goes from like 75 to like 50. Or if you remove 50% of the parameters, the performance decreases by few percentage. But what is most shocking is, if we actually started this original network with 50, with half the actual weights, and if we train them from scratch, they don't do so well. They do terribly in that task. And for a long time, people were really perplexed by this. It's like, why, right? Because after the pruning, this point and this point, they are basically same network, same structure, same architecture, same number of parameters, but this model has, terrible performance compared to this model. They have the same number of parameters, same structure. Why? Because this model started with much bigger, so it was easier to learn. So the summary is, it is very easy to train a deeper network than a shallower network. And of course, here when I say deeper, shallower, here shallower still means like, hundreds of layers and, millions of parameters. It is not, I'm not talking about, few parameter versus millions of parameters. So obviously, it is for the theorists to figure out why, right? But the fact that we see this observation again and again, it should tell us that, okay, maybe if our goal is to get a smaller network, you want to start with a bigger one and then clip it and prune it to get a smaller one. And of course, you want to use the best technique. Don't use these kind of things. APOZ means average percentage of zero. So while training, if you remember, in our first 2 weeks, we learned about L1, L2 regularization, right? So if you do L1 regularization, then some of the weights will become zero. So after network is trained, if you remove all the weights that are zero, this is what is called as APOZ. It is more subtle than that, but it doesn't work that well compared to like using Taylor series or activation means. So this is the observation. So now, how do you prune the network? So obviously, so first you initialize the model, you train the model for until convergence, or let's just say for S1 iterations. And after that, for each of the parameter, you decide how important it is to keep this parameter, right? So remember, the network is already trained, right? So parameters have changed their values since initialization. Not all parameters seem to contribute. So there must be some way to figure out the importance of each individual parameter. And then we find the worst performing ones, or in the sense, worst performing in the sense, these are the parameters. If you drop them, the model performance will not change a lot. So you drop them. And then it is important to fine tune. So this part is also important because if you don't fine tune, your performance is a lot worse than what if you would get if you fine tune. Here I'll show you the difference. So if you simply drop them after training, your performance is like this. But if you fine tune them, you recover some of the performance. So the network at this point and this point, they are the same network, except this one has learned more. So you might say, it's okay, right? We can always fine tune. Thing is, you might not always be able to fine tune. Why? Because say if Google has released a giant model, right? But it is too big for you to fit in your GPU or for you to pay to run on infra. So if you decide to prune them, you won't be able to fine tune because you don't have access to the data that Google used to train that network, right? So you can see how this is a limiting factor. But oftentimes it turns out you could fine tune on a related data set. It need not be exactly the same data set, but as long as the data set is similar, you can fine tune. But fine tuning is important. So obviously now question is, how do you find parameter importance? One trivial way would be to do what is called as oracle. That is, you take a network, you just remove one parameter, and then you now measure the performance. So if a validation set, you do an inference on all your validation set, and then you say, okay, so before if you had 70, say, before you had 79 with all of it, and now let me say all minus one, let's say the performance. So here one is this particular one, red one. So now the performance, let's say 78.5, right? It means this network contributes to 5.5% of performance. Similarly, for this one, when you do, you determine that, it goes down to 77, right? It means this neuron alone contributes to 2% of performance. So it is important to keep this, not this. And of course, you shouldn't be surprised if that the initial layers and the final layers are very important, right? Because initial layers capture the input data, final layers capture the final prediction. So typically the middle ones are where you can afford to clip them. So in this way you measure. But the problem is, if you do this, remember, you have to do the full validation set forward pass to compute this number, right? So you have to, if your network has 100, if you have 100 million parameters, it means 100 million times you have to run it on all your validation set, right? Your validation set could itself be a million examples. So that is the kind of thing that is only possible with a smaller network and smaller data sets. It is not possible with big networks. So this is what you would have to do. Now this is still greedy oracle, because it is possible that if you remove this network and then fine tune it, maybe you'll recover all the performance gap, right? So ideally you would want to do this, remove this, then fine tune it, then see what the performance is. But if you do that, then that'll even be even more expensive. So we just assume that the network is frozen and will compute the performance. This is called as a greedy oracle. At least this is slightly doable than the true oracle. And people have done that. People have done that for networks. People have a lot of compute power and a lot of patience. So on a VGG16, the kind of network which we saw, in layer 1, you see this is what happens, and layer 13, this is what happens. And by the way, you should keep a note that the y-axis scale is different between here and here, right? So here it is much smaller. So in layer 13 versus layer 1. So in layer 1, if you drop some of the parameters, the change in loss is very big compared to layer 13. Right? And of course, it tells you that initial layers are more sensitive. And but you might think, oh, VGG16, it has like 4,000 filters, 16 layers. Surely not all of it is required. Therefore, you see this. I did this experiment for my paper, and I found out that you could even have a tiny network, like this 2-layer convolution with 32 filters and one fully connected. Even then, when you drop, so here blue is for layer 1 and orange is for layer 2. Even in this case, of course, in this case, layer 1, a single neuron, single filter, if you drop the change in accuracy is like -5%, right? So it has more impact. But there are a lot of filters in layer 2 and some in layer 1 where the drop in accuracy is less than 1%, even though you only have like 64 filters, right? That tells you even on a smaller network, there's a lot of redundancy baked in. Now, question is, what would have happened if I added, dropout? Probably more dependencies, more redundancies, right? Because the purpose of dropout is to encourage redundancies in the feature, that parameter sharing. So maybe it is not about having a lot of parameters. Maybe it is the way our networks are designed and the way our networks are trained. That is what leads to this kind of overlap, or because it means here that some filters are doing a lot more than other filters, right? It's like you have a group project of 5 people where 2 people are really doing all the work and other 3 people are simply cruising, right? I don't know if it has happened with you guys, but every group project I have done definitely has been 1 or 2 people who just take all the accolades without really doing a lot of work. It's almost like this. So why is it the case? So of course the answer is we don't know how to train them in a better way. And there have been suggestions, and I have my own work where I have showed how to do this. But these things happen. Now, question is, are these 2 problems related? The fact that a smaller network, when you train them from scratch, doesn't do as good as having a bigger network and then pruning them, versus and the idea that the smaller network already has overlap. Is possible these were related? And it turns out that yes, it's kind of related. And the here, but and there is more in this work. My work paper and other people's paper have shown there are efficient ways to train, but remember they all come at some cost, right? So in my technique, you have to spend more time training. So there is at least that downside. Anyway, so I mean, I will not go more. I will not go deeper in this. But if you're interested, these are some of the really well-written papers. You should check it out. And there is another paper which was very revealing in the sense all these papers showed that actually you don't really need all the parameters. Like I said, you only need a few parameters, and but it's like a lottery where you don't know which numbers will win, right? So here the same thing, you don't know what configuration is. So think of this these lines as a sub network of this whole big network, right? So there is some sub network that is as good as the big network, but the question is we don't know a priori which of that network. That's why you start with a lot of it, and then once you have found out by pruning, it's like being able to kind of like pick your ticket after the result has been announced. It's almost like that. So if you're really interested, I'll encourage you to read this paper. It's called as lottery ticket hypothesis. It definitely changed a lot of people's opinion on how deep learning models are designed and trained, and it might also change your opinion. So I will encourage you to read this if you're interested in more on this topic. Okay, so before we move on, any question on these findings or these ideas?
Yes, I had a couple questions. Could you please go back to the graph you made?
Graph I made.
Yes, that one. So looking at this here, right, you'd have initially 32 filters, then 32 in the next layer. So am I reading this right, that depending on which is the filter count the number of filters you remove or the number of filters remaining?
Number of filters I remove.
Okay.
So we are only removing 1 filter at a time, right? So each time we're only removing 1 filter, right? So for example, out of these 64, right, there are 2 filters that if you remove them, not at the same time, each time you're only removing 1 filter, but both of these filters are such that if you remove them, the performance drop is 5% accuracy. But each time, only removing 1 filter.
Okay, I gotcha. And then a couple other questions. So with the general concept of pruning, I can see where like this would have a major impact in the training when you're going through and trying to find all of these weights, potentially millions of weights. How much does it matter when you get to just running the model, right? So say you've got, GoogleNet or EfficientNet or whatever, and it's now, it's been trained, and then you're going to run it on your images.
Mhm.
How much does it matter the reduction in complexity?
Yeah, that's a really good question. And answer is very simple. It matters a lot. Why? Because these networks, once you train them and once you deploy them, they will see millions of new data point, right? So you will do millions and millions of inference. For example, a friend of mine who works at Spotify, he told me that, their network does, I think, like close to like 10 billion predictions a day, right? So even if you were to save a couple seconds for each inference, that is like close to, like 500,000 in computation. So you can imagine it matters a lot. Of course, if you are only doing, a couple of inferences a day, probably it's not worth for you. It's for those where once the model has been deployed and then it, like for example, I don't know if you have Android phone, in their camera, they have Google Lens, right? So imagine like there's at least billion phones in the world using Android, and all of them are using this. So Google has to run all these networks on their cloud for free. So it matters a lot when when you're doing this inference again and again and again and again. So it doesn't, for each individual example, might only be saving seconds, but that seconds multiplied by billions is a lot.
Okay, that makes perfect sense. And then just kind of one last question, kind of bringing back a couple of course topics. And I realize this is related to, tuning weights, but if you could go forward just a couple of slides
Even backward, yeah.
forward,
Okay.
this one here. So is it possible to say you're trying to maybe replicate a certain behavior, or can you build out your network such that you already determine which neurons connect to each other instead of just using like a dense or something like that? You want to say neurons 1 through 5 connect to neuron 7, but 6 and 8 don't, but then neuron 9 does. I don't know, like say you're trying to replicate a particular biological system, going back to the kind of roots of a neural network.
Yeah, so people have tried that. So, I mean, obviously the idea is that if there is a winning network, the winning ticket, why don't we, why aren't we able to predict what the winning structure looks like? And turns out we aren't. For no reason other than we don't have that technique. And people have tried a lot. So eventually what people do now is like they say, you know what, let's do this as a meta learning. That is, there is another neural network. Purpose of that network is to train the structure of this network, right? So there's one network whose purpose is to do the classification. Another network, which gets rewarded, its loss of 1 and 0 is based on whether the performance of this subnetwork improved or not. So you do this, if you're interested, you should look up MAML. I think we discussed a little bit about MAML on like third week, where you use meta learning. So by doing that kind of a learning, but it is still very expensive because, if doing this one training takes you 3 hours, then doing all of this will take you 3 multiplied by, like 100, right? So yes, so there is this very brute force technique, which is still much better than humans' intuition or humans' design. So people are really bad at being able to design them intelligently. And I mean, there are a few things like, for example, even like the idea of ResNet, right? So when ResNet came, definitely, compared to VGG, ResNet has a lot less parameters. So you can think, say, in one way, they were able to solve this problem, like saying how to connect the networks. And there are other techniques, but even those were really found by doing a huge search over all the space of the architecture. So if you're interested, you should look up EfficientNet, because that model was designed with this technique where they did this, and then in the appendix they have the actual architecture, and if you see that, it's so complicated, so messy, that no human will ever design a neural network like that. But it turns out that has fewer connections and does best.
Interesting. Okay, thank you.
Okay. Any other questions? Okay, if not, then we will move to another topic. Another topic which, I don't know if you guys have seen or not, but it's very interesting, and I have done some work on this, is it turns out that these deep nets, even though they are so good at being able to do all these complicated tasks, uh, they are actually really bad at, they are really bad at really knowing what is going on, right? For example, this image on the left, when this was predicted, like if that is if you give it to some state-of-the-art model, it and it currently predicts that it is Indian elephant with 99.7% confidence. It's very confident it's elephant. Now, if you see the image on the right, to you and I, this is still the same image, right? There's no difference. But now the model predicts guacamole with even better confidence than before. The only difference is I have added some noise to every pixel, but the magnitude of the noise is so small that doesn't really change the image, right? Because our human vision has some tolerance, right? Well, like, in reality, the space of colors is like billions, right? But we can only tell apart so many colors, right? So visually, it's same to humans, right? But in reality, pixel to pixel values are different, but the difference is not big enough for us to say it's a different thing. But for a network, it turns out it's really different. And now you might say, oh, how did I come up with this noise? That's where the key, like there is, this noise was artificially designed, but you can see how, in some critical applications, if somebody were to really try to take advantage, they can, take advantage where, if say it is used for cancer prediction. So if they had access to your image, they could do something to your image where to a doctor, if you didn't have cancer, it still looks like normal, but the network might now say you have cancer. And now you can imagine you start taking all these medications. Obviously, as of today, humans are still required to verify these things. But obviously, the whole point of building all this AI is that at some point you will hand over these decisions to AI because they are so good and they are so much better, or they are so much faster. Maybe not in cancer, but there are other so many applications where decisions have already been, left up. Like, for example, the Tesla self-driving car, right? It is driving by using the AI, and for example, they're reading stop signs, they're reading the cars, and there is a paper which shows that you can put these invisible stickers on the stop signs. So when you put the sticker on a stop sign, no human can see because it's like a transparent sticker. But now the network that was earlier able to identify the stop sign thinks it's a speed limit of 80 sign, and then the car will just go at the speed of 80. It can be dangerous, right? It can be lethal. So this is the kind of problem that exists. So I will show you how to actually make this noise, but these are called as adversarial attacks. So there's two types of attacks. One is where you have access to the network which you're trying to fool. So these are called as white box attacks. And then there's another one called as black box attacks, where you can attack some unknown network. Say like Facebook's. Each time you upload a photo, Facebook will do the the classification, the captioning. But of course, you don't have access to the actual network. But even those networks, you can attack them, but they just take more effort. So say this is a network, right? We have seen this. There is a bunch of convolution layers, pooling layers, then some frequency layers, and there is a loss. We are trying to minimize the predicted Y versus the ground truth, right? And then what do? Then we compute the gradient with respect to the loss, and then we take us, and then this is the gradient update, right? This is the SGD. That is the new weights is old weight minus some learning rate and gradient. So we are taking a step which will minimize the loss. So we are taking the gradient descent, right? Now it turns out all you have to do is change that gradient descent to gradient ascent. So now instead of going in the direction which minimizes the loss, you go to the direction that actually maximizes the loss. And instead of changing the weights of the parameter, you actually change the input itself, right? So you imagine for time being that this image is also one of the layers, right? And each of the pixel are the weights. And then now if the way we did backward propagation, you do that, don't update any of these weights, only update the weight of this layer, which is the image actually. And instead of doing gradient descent, you do gradient ascent. That is, instead of decreasing the loss, you increase the loss. That's all you have to do. You do that, And now suddenly the, the classification of this will change, right? Because you're going in the wrong direction. You're intentionally taking a step where the loss will be higher, not lower. And just doing this is sufficient to, make a difference. So now you can say, you can even actually say, oh, you know what? So now, so in order to do this, you need some class, right? So you'll say, instead of using the true class, you say, you know what, I will use the class guacamole. So I'll say, okay, make it go towards guacamole. So doing that kind of stuff, gives you these kind of attacks. So in this case, we're not actually updating the weights of the network. Network is frozen. We're updating the image, each of the pixel values by a small magnitude. So here, instead of using the learning rate, which is a very small number, we use this epsilon, which is also a small number, right? So in essence, X is very, very close to X because we're only adding a small value, but that is enough to change the output of the model. So that's how it works. So instead of gradient descent, it's gradient ascent. So that's why instead of minus, it's plus. I know this is one technique. This is like the most vanilla technique. This is called as fast gradient sign method. So all we have to do is change the sign, get the gradient fast. And these methods are good, but the amount of noise you have to add is maybe more. But then there are other methods where you, instead of taking one big step, you do take a lot of small steps called as iterated method. There are other techniques that are slightly more complicated. I will not go into those, but there are many different techniques that have been designed. They all take advantage of you having access to the network weights, and you have the access to do the backward pass, right? To do the back propagation. If you can do that, you can easily fool. And if you, I didn't include this in the projects, but if you guys are interested, you could take one of these things as a final project and try to implement one of these algorithms. So, and now obvious question is, what can we do about it, right? What can we do to defend against these adversarial attacks, right? Obviously one is, let's just make the models more robust. That is, making small changes should not change the prediction of the model, right? Because yes, this image may not be exactly this image, but it still looks like an elephant, right? So if human eyes aren't fooled by this added noise, why should the neural network be, right? So instead of having a network that is very sensitive, you make a network that is more robust. So this is where, so what you will do is during training, you will actually add these kind of losses. So during training, what if I took this image, call it an elephant, also added the adversarial noise, and even though now it's guacamole, I call it an elephant, and during training, I also train with these adversarial images. It turns out this kind of works, but not good, because the space of adversarial attack is very, very large, like small changes and every pixel can be changed here and there. You have to do a lot of work to do. And so Google actually trained like really, really expensive model. It is slightly better, but it can still easily be fooled. So theoretically it is useful, but not practically. The other thing is, can we look at the image and can we do something to the image itself? Even though we know some attacker has manipulated the image, we can try to bring back the image. We can try to remove the noise, remove the perturbation added by the attacker. So this is where either you do the image transformation. So it turns out doing some transformations to the image recovers these kind of attacks, or you try to remove the noise. So you do denoising. JPEG. Sorry, this paper actually includes, because this is a slide from my paper. So I will not talk about my paper, but I have an idea. I don't know how to do this, or denoising. But I will tell you that surprisingly, somebody found out that simply doing a JPEG compression on top of the image almost gets rid of these adversarial noise, right? Why? Because this noise is really carefully crafted. It has to be exactly like this. So when you add this to the image, now if I do a JPEG transform, now I don't know if you guys know about JPEG transform, but it is done on a frequency space, right? That is, you do a DCT, you do a cosine transform, and on a frequency space, you do the quantization, and then you go back to image space. So converting this to frequency space and then back to image space kind of ruins this noise enough that this noise no longer is meaningful and the network is not fooled. Here, let me show you an example. So here, this is one image, right? So this is this elephant which you saw before. Here's the guacamole. And now here's a step, this image, but this is adversarial image, but we did a JPEG on top of it. And now the original class is back, Indian elephant. One thing you'll notice is the confidence has gone down significantly. But for most of the applications, we don't care about the confidence, we care about the class. So we have kind of recovered. And like at the same time, 3 different groups kind of discovered the same thing. But there's only so far you can go with JPEG. So here now question is, with JPEG, you have this knob, right? How much compression to do. So the more compression you do, the more you are able to recover. But there's at some point you have done so much compression that the image, the quality goes so bad that the accuracy again drops, right? So sorry, here the green is actually original image, that is no adversarial attack added. So here performance is supposed to be 80 all the way, but as you can see, as you do more and more compression, slowly performance goes down and suddenly falls the cliff. This red, blue, and orange are the adversarial images. So some adversary has taken the image, made some changes, so reduced the accuracy. So see, even the adversary was not 100% successful. They're only 20% successful. And now in these images, once you start doing JPEG, you recover the accuracy. You never go back to 80% because not 100%. It's not foolproof. But at least 20 to what this looks like 60, at least 60 or 65 or 70. So as you do more and more quantization, you recover more, but again you fall off the cliff. And this cliff is because JPEG is also designed to really ruin the image. So it kind of works with limitations, but not to the satisfactory level. So if you are in doubt that if somebody has given you an image and if you're trying to run through a network, you will be safe. A safer bet is to do a JPEG and then run it. So because if they didn't do any perturbation, the performance won't be as bad, right? It will be instead of 80 to 77. But if they have done the attack, at least you'll recover. More, chance of being fooled is less. Okay. Any questions on this problem or this solution?
Quick question. Is it common, so like say in the ImageNet example where you have, like I think it's 10,000 classes that it tries to predict from, is it common to have an I don't know class or like some sort of because in some cases I'd rather just my model tell me I don't know what's going on here versus my model saying that it's something that it's not, right?
Yeah. So what you are asking, is something, seems very easy thing to say, like easy thing to contemplate, but practically it's actually really, really hard, right? So here, let me, so what you are saying is, when we build a classifier, right? Say, I have a cat versus dog, right? It's like a really popular network, right? So a popular application, there is a data set on Kaggle. If you're interested, definitely play with that data set. We'll teach you a lot, right? So when you build a binary classifier, right? So what we do is we take some probability value and we do a sigmoid here, right? Like this, right? So because this is a continuous value, right? And you will pass this continuous value through a function. Now in this case, it looks like a hard step function, and that is what softmax is supposed to be like, right? But because it's neural network, instead of being a hard step function, it's a smoother one. But anyways, we have a threshold and we say this means class A, this means class B, right? Now, how do you make none of these? Because it turns out it is very, very hard to do, because you only learn about the features. Because this is what we talked about in our first few about these, last things about these are discriminative models, right? Their purpose is to build so think of it as like you have all these points in this space, trying to put a hyperplane, and then everything that is on one side of the hyperplane is one class, and everything that is in the other side of the hyperplane is other class. Doesn't matter where the points are, right? So here, let me see if I can. So if we look at this, here the the colors might kind of fool you. What if there is a green dot somewhere here? So what if there is another green dot, but it is here, right? So you might be tempted to say, well, you know what, this point is really far from these points, so it is possible that this is neither green nor red, right? But these models aren't designed to do that. These models are only designed to learn this line. These models have no idea where which red point is further from which red point. These models are really designed to find this line, right? And then the decision making is not part of the machine learning. Decision making is the arbitrary post processing that we do, right? Once we have learned this line, we say, okay, every point that is under this line or off this line. That's how we get two classes. In order to say neither this nor that, you can't be just learning hyperplane. You have to learn what is called as the generative model, right? This is what we remember. We talked about different generative and discriminant model is you need to somehow be able to say, oh, all my green points are here and all my red points are here, right? And all my red points are here, and therefore I know what it means to be a cat. I know what it means to be a dog. So if you train a GAN on all the cat images, and if you pass in not a cat, probably GAN will be able to capture it. So you can then make one GAN for cat, one GAN for dog, and then once you have this new image, pass this through both of these generative models, find out if they are either cat or dog, and if they are, if the confidence is low on both of them, probably you can tell it's neither. But you see, that doesn't scale, because if you have 1,000 classes, you have to build 1,000 generative models. I need a lot of data to do this. So what we're asking is a very, very fundamental question. And there's a TV show called as Silicon Valley. They have this thing called as Hot Dog or Not Hot Dog. And in that, they actually make a fun of this, because they build a classifier to say hot and hot dog, and then they pass all absurd sort of stuff, right? Because everything that kind of starts to look like hot dog will be called hot dog, because the network is really designed with yes or no. It doesn't know anything in between. So in short, the answer is that is a true solution, but it's really hard to do unless you are building a generative model, not a discriminative model. Yeah, well, I mean, otherwise people would definitely do this. And building a really good generative model is really hard, because our ability to make such generative models is limited by the kind of the data and the kind of the training process we have.
Thank you.
Any other questions, folks? So so next time somebody says, oh, deep learning can easily be fooled, at least you will know what they're talking about. Okay, now let's get to one really nice application of deep learning, that is, can deep learning be useful in image compression? I know this is a very esoteric application, you might think, but image compression is really widely used. Every browser, every cell phone, like when you take a photo, your photos are not stored as a raw pixel value. They are actually compressed. Now, whether they are lossy compressed or lossless compressed, most of the time they are lossy compressed. So compression happens every time you take a photo, every time you send, like each time you send a photo via Facebook, Facebook will do its own compression, right? So now question is there somehow we can use deep learning to improve the compression? Now question is, why would you not want to? Now there are some techniques that try to use deep learning as a compression algorithm, right? And this is not that's not what I'm going to discuss, because the problem with that is, you saw the forward pass takes a couple of seconds, right? So each time you have to open an image, if it would take a couple of seconds to load the image, you would be unhappy, right? In your phone or in your laptop, each time you double click a full image, it opens instantaneously, even though it is stored in a compressed format, because the decompression is so easy, so quick. So JPEG is so widely successful for that reason. We are so fast to decompress. So in this particular technique, goal was like, can we still maintain the speed and convenience of JPEG, but somehow use deep learning to improve it? Because JPEG is really blind, right? Because the way JPEG works is it takes 8x8 small window of image and just compresses those 8x8 without knowing what is there in the image, right? And so, for example, let's look at this image, a nice image, right? And there's a lot of things. And every 8x8 block, right? 8x8 is a very small, right? 8x8 pixels is just compressed, assuming they are all equally important. but it's not equal, right? The images have foreground, images have background, the images have people. Some things are more salient. That is, you as a human, you will care about the quality of some parts of the image more than the other parts, right? So for example, let's look at this center pillow here. I mean, compared to this wall, you would definitely want this part to have a higher quality because that draws your attention right away. So, between, so if you do a standard JPEG to get the same amount of size, this part will look like this. What if you could keep the center part as good and as high quality, but the other parts you could compress? It means you have to know what parts are more important and what parts are not, right? So somehow we could build a map over this image that would tell me, what are the interesting bits? Like, what are the things that I want to keep high quality and what are the things I want to keep low quality? Instead of simply relying on the frequency, because here, typical JPEG relies on the frequency. If there's a lot of changes, it will compress less. If there is less changes, it will compress more. But that is not semantically useful. That's not aware of what the image contains, right? So I want it to be semantically aware. So how do we do this? So again, I will quickly go over this idea. So here on this image, what you're seeing is, if this is a photo, and there are these tools where you can actually, it's like these special classes you give people, and then when they look at part of the image, you know exactly where they're looking at. So this is what you call a human fixation. So when you look at it, like if you look at this photo, I don't know if it's true for you or not, but my eyes were immediately drawn to this part where this girl is trying to blow some bubbles, right? So clearly this is where my eyes focused. And there's this another, so you guys learned about these activations, right? The intermediate values are activations. So if you were to take activations of the image, and then you generate something like class activation map, and if you're interested, Google, it's a nice way where even Keras will give you this, where given a model and given an image, it will tell you what a class activation map looks like. That is where what are the parts where model has a higher value. So it turns out, so activation map is very similar to human fixation. But this might not be enough, because this is just fixation for the first second, but once you have seen this, immediately you'll also realize that, oh, there is a boy also here. So this model failed. So in my work, I kind of made changes to this structure. We call it multi-scale region of interest, where we find all parts of the image which might be more salient, and should therefore have a higher quality. And so this is called MSROI. And here's some mathematical difference between MSROI and CAM. And again, if you're really interested with the paper, or I also have a video of the whole talk I gave on this topic. Again, I'm happy to share that. But in essence, I'm saying that this output is better in order to differentiate which parts I want higher quality and which parts I want lower quality. So blue pixels will be the ones where I'm willing to sacrifice the quality over compression, and red would be where I would rather have the quality and not the compression. So once you have this map now, and then you have JPEG. Now, how do you combine this, right? Because JPEG doesn't work like this, right? JPEG just takes every 8x8 blocks, does a DCT quantization back to an image. So this is a typical JPEG pipeline, right? So you split the image into 8x8 blocks. To the DCT quantization means just quantize the values by some factor, and then that factor is called a scaling factor. That's what we saw in that earlier plot, where we went from 100 to 0 in that adversarial images. And then you do entropy encoding, like your run length encoding, just to if you have like 5 zeros repeated, instead of saying 0000, you say 50. So 2 bits, like 2 points, numbers representing 5 numbers. So when you do that, you get JPEG. So what we do is, say you have this image, and then you have this map over the image, right? And this map, has different, values, and value goes from 0, that is blue, to 1, that is red, right? So first, let's change this continuous value into discrete bins, right? So, let's just say we only have five different levels, right? So the most important, least important, and and in between. Now, each of these blocks, these 8x, because remember we talked about that JPEG works independently for each 8x8 blocks. So each of these 8x8 blocks will go through JPEG encoding separately, and this Q factor, the scaling factor, will be different for each of these blocks. So if it is a very important region, you have a high Q, means less quantization. And if it is not important region, you have low Q, it means more quantization. It means these things will have poor quality, these things will have high quality. And then you put them back together. And then see, but the problem is when you do this, the image which you get is really a Frankenstein monster, like really combination of all these different thing, and they don't look smooth, they don't look continuous, right? Like when you see an image, like wow, it really looks like a Lego block, like a jigsaw puzzle where you can see the pieces. So to make it a final smooth, you do one more step of JPEG, so that it smooths over the differences between the blocks, and then you get an image which now looks very similar to original, but we know that some parts have a higher quality than other parts. Now it might not be, these are all done at a scale where it's impossible for a human to tell apart. So that's why we use some quantitative numbers, some metrics to really compare them. But if you compare them, you will get your results. So again, step by step. So you use your MSROI first to get a heat map of all the objects. It's a standalone process. You don't need the image. So you don't need to do JPEG while you get the MSROI. Once you get the MSROI, encode and then decode. So what does the numbers look like, right? And I don't know if you're familiar with PSNR. PSNR is like the quality. Higher the PSNR, better the quality. So you can imagine. So you can see the overall PSNR of the image between JPEG and normal is very similar, but PSNR of the parts we care is very different. So the important regions have a much higher PSNR than it means we are redistributing the quality, right? So overall, the file is still the same size, right? But the quality of some part is much better than the other part, right? Because you can see the PSNR of selected regions, salient regions is much higher than the PSNR of non-salient regions. And these are some of the other metrics used for image comparison. I'll not go over them, but this is some technique. And it's very hard to make improvement on JPEG because it's like a 30-year-old technology where plenty of research has already been done. So it's like saturated. So when we came up with this idea, a lot of people were impressed because people had given up on any possible improvement of JPEG. Because see, the best part of this technique is in the end, you get a JPEG image. So to decode it, you don't need any of this fancy deep learning neural network or MSR. You just decode as if it were a standard JPEG image. Right, so you have somehow added the value of deep learning without changing how the images are decoded. So you still get a very fast inference, but you no longer have this blind approach to comparison. Any questions on this? And again, for all my papers, if you go to my GitHub, I have the codes. The problem is this is, like 5-6-year-old research. So I don't know if the code will work with the libraries of current version, but probably if you're interested, I could help you in running them. But I'm sure there are like other people have done other interesting work related space. Okay, now, let's come to even more critical application. And this is where I was, I worked at a company where this is what we did, and I worked for almost 4 years, where given these images, right, microscopy scans, can we detect cancer, right? Now, let's learn a little bit of background. So these images are basically, if doctor suspects that you might have a cancer in a certain part of the body, because of the blood test or some symptoms, they will take a needle, they'll take a small piece of the tissue. This whole thing is literally, smaller than a grain of rice, right? They are very small, like very small piece of a tissue is taken, is put on a slide, and is put on a very high magnification microscope. It is so high that this thing, when you scan it, the image is like billions of pixels, so that they are like gigapixels, right? So this is like if I were to blow this image to the native resolution, I would need 2,500 monitors to really see all the pixels, right? So they're really big images called as whole slide images. And so now here, people are, doctors, pathologists, they zoom in, zoom out, and find the regions of cancer. So these are called as whole slide images. Now, But the thing is, if you do have a cancer, it's not that every cell, every pixel will have cancer, right? There will be regions where there is cancer, there's regions where there is no cancer, because a tissue has many different parts. They have some parts of the tissue are support system, like for example, this part, all this red, these are your blood cells, that's why these are red. Then you have these, fibrotic regions, they are like, support, they provide nutrients, and this is where you have this epithelial, these are the tissues that actually do the work, and then you have other cells that actually have the cancer. So even though this person has a cancer, doesn't mean all of this image, every single part will have cancer, right? So there's only some parts will have cancer. Now, I don't know if you have realized, but how do you train a neural network where, because if I give an image of a cat, yes, not every pixel belongs to cat, but the whole image is a cat, and you can fit that image in your model, in your GPU. So just say this image is a cat. But this whole image will never fit in a GPU, right? These images are like 50 to 100 gigabytes. So you can't train on the whole image. It means you have to take parts of the image. So you will take, say, you will take this. So you'll say, oh, you know what? I can't fit the whole image. Maybe I can only fit this part. So you'll in that way you will try to do. This. So so you'll take this part, you'll take this part, so maybe, and the question is, if you only take 3-4 parts, maybe you'll miss out on a cancer reason. So I will do like we did with convolution, where I will really take a small part and I will do a sliding window where now this part, then I will move it by 1 pixel, then I'll move it by 1 pixel, and then similarly I will cover all of the image, but I will take 300 by 300 or 500 by 500 size, but I will really make sure that I cover all of the images. But now the problem is, what label will you give to each of the individual images, right? So let's call these individual images as patches. That's what people use. That's the word, patch, because the whole thing is image. So each individual thing is called as a patch. And because it's very important, because you will soon realize that machine learning is not mature enough to solve this kind of problem. So say this whole image, and you split them into patches, and say you have 10,000 patches, right, in the whole image. So 10,000 patches makes all of the image. Patches equals to 1 image. Now, out of these 10,000 patches, it's very likely, and based on my experience, only a fraction of these patches will actually have a cancer. So let's say that only 100 of these patches actually have cancer cells. I think that is, it has things that look like cancer. And the remaining, 9,900 patches don't have cancer. But remember, this patient has cancer. Now, question is, you want to say, oh, I just know which patch. We don't know which patch has cancer. That's the whole purpose, right? Purpose is we just know this person has a cancer, and we don't know which patch has cancer. We can't find. Of course, you can ask some human to say, oh, human, go to look at every single patch and tell me. That would be impossible. Why? Because this is just one image. There's like millions of images. Actually, this 10,000 is just like a low number. Typically, it's like hundreds of thousands of patches per image. So you will not be able to, no human. Remember, like you can't send. Typically, when people get annotations these days, we have all these services like AWS has this Mechanical Turks, there's Label Box, all of them, they send this to, developing countries like India, Bangladesh, Vietnam, where people, work for pennies, and they sit and say cat, no cat, truck, road, no road. So they can, annotate roads, trucks, cars, trees. They can't annotate cancer, no cancer. So for this, you need like some expert, and these experts, they are also real doctors. They have to look at real patients. They don't have time to sit and tell you cancer, no cancer. So annotating every patch is impossible. Like nobody can afford, and nobody can even fathom doing that. It means you don't know which of the patch is cancer and which of the patch is no cancer. And very likely that a random given patch is not a cancer. So how do you even train a model? Because remember, if you in the CNNs, we know that each image, each patch has to have a label. So if I say, what if I consider all patches in this image to be cancer? Problem is, see, 9,900 patches doesn't have cancer of this slide, but the slide which actually doesn't have cancer, the negative case, even in that, so in that all the 10,000 will not have cancer, right? So it means between cancer, no cancer, if I really collect all the patches from all my data set, almost all the patches will not have cancer. You will not have any positive examples, and you won't know which one of it. So it is impossible to train a neural network or deep learning where you have so much of label noise. That is, you don't know which, because if you call all these patches as cancer, you are basically saying you're taking 9,900 patches, which doesn't have cancer, you're calling it cancer, right? And there are other 10,000 patches which doesn't have cancer, you are calling it no cancer. But these 10,000 and these 9,000, they both look alike, right? Because if it is blood cells, they look like this, whether you are cancer or whether you have cancer or don't have cancer, they look alike. But sometimes we are calling them cancer, and sometimes we're calling them no cancer. Imagine like training a neural network where you have cats and dogs, but 90% of your cats are actually labeled as dogs, right? That network will never converse. And if you are not sure, I will encourage you, go home, take that cats and dogs data set, just write a script to manually change the label of 90% of cats to dog, and see if that model learns. That model will not learn, because that will see a cat and see the label dog, it will think that is a dog and just learn everything is a dog. So I hope I have done enough justification to tell you that any standard technique on whole slide images, this passage will not work. It is not going to work. So what do we do? Right. So this is where this idea comes about. This is where I think this new idea called as multiple instance learning. So before each of the paths, when a patch has a label, each patch is a single instance, right? So, and in each instance has a label. But we don't have label for each instance, right? We only have label for a group of instance, right? Here, group being a group of all the patches in this image has one label. That's true. That label is true for the whole group, but we can't tell which instances within that group is positive or negative. So this is what we did, right? Typically, this is how we train a model. That is, each point is either positive or negative. What if you have collection of points, and then that collection point is called as bag, and that bag has a label, but inside the bag you don't know whether it is true, whether it is positive or negative. That is, you can see this circle, this bag is called as positive, but it includes both positive and negative examples, right? Similarly, you have some negative bags. Now, should a negative bag also contain a positive example? Probably not, right? Because if positive means cancer, even if I have a bag of 100 patches, even if one patch has a cancer, probably the whole bag is a cancer, because cancer means it's cancer, right? So this is where idea comes about that. Typically, negative bags don't have positive examples, but positive bags have negative examples. Or in a better way, let's let's look at this image of say we are trying to make a classifier on whether it's ocean, right, or a beachfront, or it's a desert. Now, if you see a sand, now say these images are really, really big, like these are like not small images, but they're like satellite images where they're so big that you can't fit in the whole image. You have to take a small part of the image. So if I take a small part of an image which has like this, and if I were to take this part, and if I see sand, and say, oh, because it is sand, therefore it is beach, sorry, therefore it is desert, would be wrong, right? Because sand is also there at the beaches. But if I see a water, definitely you can be sure it's not desert, right? So that's where the positive negative example comes in. If you're really interested, there's slight difference between strong assumption versus weak assumption. Strong assumption means even if you have a bag of 99.9% examples negative, one positive, then you will call it a positive. But you might imagine, there maybe even a desert, there could be a small patch of water, like somebody could have just dropped some water, or it could be a mirage. So most of the time in reality, people use a weak assumption where if there is more than a certain percentage, or if it's like a weighted combination. So if there is sufficient number of positive examples, then we call it positive. Otherwise, we call it negative. Or the other way to look at it is, if I give you a bunch of, like if I give you a keychain with a bunch of keys, and if I tell you this keychain has the key that opens the door, right? Now, how do you find out which key is that opens the door, right? So basically you look at, so if I give you this and then you try all the 3 keys, oh, it doesn't open. And then I give you another keychain, and he tries all 3 and it opens. and then I give another keychain, and that also opens. So now, of course, in this case, it seems, oh, wait a second, green is the common one. But imagine instead of just being 3 different colors, if you had, hundreds of thousands of different colors. So in that, how will you determine which is the key that actually opens the door? So it's almost that kind of a thing. So this is what I call multiple instance learning. And a lot of techniques have been designed. I will not go over all of them. I'll just give you one, the most popular technique, right? So, the idea is very simple. Idea is you take a bag, right? So you don't know which of the patches are positive or negative, but a bag of patches coming from a positive class. Remember, so we know that positives, we know a slide is positive, right? So I will make, so let's say, second. So let me make, a bag of lot of, patches from this slide. And typically, you will, if you're not doing exhaustive, that is, if you're not doing all patches, then, you will probably take, then you will have a diversity. You will take from all parts of the image. So now I have a new bag of all these patches, and that bag will have the label that, that is same as the label for the whole slide. Whole slide belongs to a patient, right? So that patient is either cancerous or non-cancerous. So at least we know that, right? So now we say this bag has a label of cancer. Now, since it is possible that only one of these patches in that bag is cancer, but doesn't matter. We'll call the whole bag as cancer. So how do we train such a network? So to train such a network, so you say you have this bag of instances. Now you do this feature extractor the way you guys did in your second assignment. And now you just assume for that whole bag is your one example. And you might think, oh, wait a second, I gave all this talk just to say that, oh, I just treat a bag as an example, and that bag, and turns out it works, but then you throw in the attention unit the way we studied for NLP. But in this case, it is important to have attention, because attention will tell you, will basically help you find the green key, right? Because initially we don't know which of these works, but while training, attention is basically trying to add some weight to each of the instances, right? So here, so say there is, let's say attention vector is, this is A1, A2, A3, right? So this has, this is your instance one. So this has value W1, W2, W3. So initially W1, W2, W3 are all different, and A1, A2, A3 are all the same. But as you keep training the network, and remember for this whole class, we have given the label opens, right? So but we don't know which one is opens. But as you see, more and more examples where, the network starts remembering from via attention that, oh, the green, if there is green, there is more likelihood of it opening. Initially, it doesn't know, right? Just doing some statistics correlation. So over time, the attention values for A3 will increase, A2 and A1 will decrease. So if you keep training, of course, this depends that you have a lot of examples, a lot of data points, right? So once you keep training over time, eventually A3 will be higher and higher, A2, and then post fact, when you do the analysis, you can simply drop the low attention values. You can keep the high attention value, and therefore, if you do that, it turns out it is able to find the cancerous patches. Right? Because remember, we already know the patient is cancer, but we have to find out where is the cancer. Otherwise, it's not, because if the doctor says, oh, yeah, you have cancer, but I can't tell you where exactly where, you will think that doctor is a scammer, right? So you want people to know. So we want people to find the patch that has the cancer. So by doing this, by adding this attention, and attention is slowly learned, there is some correlation. So because of correlation of green, we start adding more and more weights on the green. So imagine if I were to take average of all the positive examples. If I take average of positive examples, probably I will have higher value for the green than the other ones, right? And if you do now, in this case, it's possible, there's only 2 examples, so there's both orange and green have the same value. What if I have another key with green, black, and let's see, yellow, not yellow, let's call it gray, right? So now if you take average of all three, green will have the highest value, right? So that's how by doing that correlation study, it will eventually learn to attend to the right instance, right patches. So the most popular technique in this space is called as attention-based deep MIL. Really well-written paper, easy to understand. So if you do this, the whole architecture is very simple. Take an image, make a bunch of instances, call it a bag, have a feature extractor, have a attention, and then over time, and once the network has learned, you will learn that attention, and when you go back, you'll be able to find the patches that have cancer. So that has actually worked out very well. Here, because we have some time, I'll show you one new paper we have. This is a paper I wrote while I was at the press conference. So now we actually even improved upon it by using, again, I don't want to get into this whole idea of like Shapley values, but if you're interested in like interpretability and all this stuff, because it turns out it was hard to interpret these kind of network because you only get like so you don't get a hard attention, right? I don't know if you guys remember we talked about soft and hard attention. You'll only get like weights, right? So you will get, A1, A2, A3, where A3 is higher, A1, A2 is lower. So you just know that, oh, this has more likelihood of cancer than these two, but you never get a clear difference, cancer, no cancer. But that is not useful for doctors. They'll rather have, which is cancer, which is not cancer. So we designed a network which is really able to, give it more interpretable output. And I'll show you some examples. And so, for example, in this plot, here we are comparing the bottom one is the attention. So you can see it's all over the place. But in our technique, it's very, very simple, right? So, green is one type of cancer and blue is no cancer. We have like very clear separation of, probability and it being cancer or not. So we were able to, and you can see here, this each individual plot is like, one patch that we're able to identify whether it is cancer or not. And we actually even did a correlation study. We even asked real doctors or experts to say, hey, can you tell us exactly, what parts are cancer? We could do that with few slides, if not with all of them. And in those slides, we were able to show the correlation that with the pathologist, was asked to evaluate the heat map based on the following question: which heat map out of the two would you prefer to use, AI plus human one? And then all of them said that, they would rather use this one because there was a higher correlation between, where experts found the cancer versus where the attention model found the cancer. So by doing this, we're able to find the exact places where, and of course, this is still not, so it is still like, it's better, much better than before, but still not where, I would be safe. Like, I'm like, oh, you know what, let's just stick with this. We don't need people. No, we still need people. We still have a long way to go, but we are getting there by being able to identify and, you might be thinking, maybe there are other ways to find these reasons. So, this whole area is called as weakly supervised segmentation, right? So where, here, let me show you. Because if you go back to this image, right? Because I told you that, if you do like class activation maps, you are able to, now in this case, it's fine this, but if I were to tell you, do a segmentation of, people and, foreground or background, but during training, I don't give you any examples like that. Right? Because, to do segmentation, you need a label for every pixel. I only give you a label for the whole image. So by doing this CAM, classification map, you can see how this is a poor man's version of doing segmentation, right? So this is the whole idea is called as, weakly supervised learning. So this is a whole field of deep learning where you do get some labels, right? But labels are not as dense or as meaningful as the predictions you would want to be. So labels are only at the image level, but you want the output at a pixel level. So this whole category of a task are called as weakly supervised learning or weakly supervised segmentation. And this is what we are doing, but especially with the really, really large images, the way to do it is by using an ML based technique. Okay, that's all I had. I intentionally wanted to leave some time in the end if you guys have, more questions on this or on assignment or on the project. I'm here to answer them. Any questions? So, there are plenty of other topics we definitely didn't touch. And I will encourage you guys to explore on your own. If you read the book, the textbook, it also has some more examples, some more advanced topics. Definitely, explore them. And the best way is to really, play with the code, play with the solution, and see if you understand what is going on.
So, oh, Sensor has his hand raised. Sensor, you go.
Yeah, thank you, Kyle. I had a question regarding final project, and I discussed with you, Professor, that in my data set I have a mix of numerical and categorical features. And my question is, how do I feed the input into two different layers so that will the network know that when a subset of features is fed as numerical and a subset is fed as categorical, being like one hot encoded, will they, like, how do I split the data set, and how will the network know exactly that will it do what I mean?
Yeah, so that's a really good question, and that's a very practical problem, right? Because in reality, because all the other examples we saw, those were like academic data sets, right? So they're very nice, they're well structured. The data set you are working with, is a real world data set. Therefore, you have different modalities of the data, right? And it happens in other space also. So this is, so now the question is, how do I differentiate? So the way you differentiate is because, so what happens if I don't do this, right? So, let's just look at the basics, right? So can I move all of this? I can move all of this, right? So let's say, if I simply if I just don't make a difference between ABC, or if I simply, let me see if I can. So if I simply have one dense layer, and if I simply assume, that is, if I put them together, right? That is a query you have, right? Why, what is the downside if I don't do anything separately with them, right? If I simply, assume they're all set of features, and if I just have one dense layer that's really big, takes all the features, and I mix them, I put them together, right? What is the downside, right? So the downside, if you do this, so first of all, this already works to a good level, like you don't have to really worry. But, of course, here our goal is to get as good a result as possible. Now, what is the problem if I simply throw all different, like the numeric data, categorical data, binary data, or, text, images, if I simply throw them to this one dense layer? Because remember, what does the dense layer do, right? So dense layer has, connections from everywhere to everywhere, right? So, this has connection here, this has connection here, all these features, they all have, very connection. So this is what we call as interaction, right? So there is an interaction between this feature and this feature, right? And there's interaction between this feature and, this feature. Now, problem is, if these values are not of the same mode, right? Here mode means like a modality, right? So in this case, modality is like numeric, might have different range, different meaning, because, in numeric value, 3 is greater than 4. Sorry, 3 is smaller than 4. It makes sense. But if I have a number, if I have, like, I have a car, cat, and a dog, there's no reason to say dog is greater than cat. That doesn't make sense. So if you simply do this, then you are kind of confusing the model, and model has to learn all these variance or inter-scaling, and this doesn't work very well. The solution, it turns out, is to do this. But can I scroll? How do I go to the other side? I guess I can zoom out. Okay, perfect. So what the best solution, I mean, it's not the best solution, but at least, much better and easy to implement is you have one layer, one dense layer, which only takes in data of that modality, right? So your, all your numeric data that could just come here. So your numeric data is just, let me, this goes all the way to here. Now that we don't need it, this comes here. Now we can zoom in. Okay. So your numeric data is here. Say your categorical data is here. And your, let's say your other, let's say Boolean values are here. Now, if first dense layer, there is no interaction between A and B, B and C. So this is where, so what is this space, right? So this area, this space is called as the raw space, the pixel space. So this is what we talked about, right? This is the raw space. And this is the feature space, right? This is where this is like the embeddings. This is the, the feature values. So you allow the interaction once you have converted them to some feature space. And then now, you concatenate them. So now you have this one, vector. And from here onwards, you add your standard dense layer and, convolution layer, or, just multiple dense layer, because in this case, data is not images. So you'll not have convolution layer, you'll just have dense layers, right? So you have a dense layer here, you have a dense layer here. Right. So now, here, of course, once you have the dense layer, you are going back to the problem that is going to be interaction. But the interaction is not happening on the raw space. Interaction is happening on the feature or latent space. Why this is better? This is better because if, let's say, it turns out that these values have to be normalized differently than this so that they can interact, these dense layers can actually learn to do that, right? Because you are doing a joint backpropagation. When you do the backpropagation, you are going from here to here. So any weights that is being learned here, right, is being optimized to maximize the interact. There are no hand-free drawing here. So the weights here are being optimized to maximize the interaction here. Because here, this is where all the interaction is happening, right, between these features, right? So here, this interaction is being, whatever will maximize the interaction between the features here, these values will change accordingly. So this is how most people do it when they have different data, and this is very easy to do. But however, this is not the end, because if you know more about these different modes, you can do, like, for example, if one of them is a text, you can convert it to using Word2Vec. If one of them is images, you can convert them using ResNet. If one of them is your sound, you can do like a spectrogram and then convert to image embedding. So the more you know about the type of the data, the better the better individual layers you can do. But it is important to make sure that these are trainable, right? That is, because you don't want these layers to be frozen, because if these layers are frozen, then these don't have the ability to change them to maximize the interaction. So if you do this kind of structure, it will help you really learn how to interact between these layers. And in fact, the weight values which you will learn here will tell you. So for example, if it turns out that let's say this has a very low values, this has very low values, this has very high values, it means your network only will realize that only numeric values are really useful in doing the task, and this is not. So it minimizes the importance of these two, and it maximizes the importance of this. Does that help you understand?
Yes, and moving from the concept into implementation. So do I create 3 different arrays? Like I will do, if I load the data set, then I would create like 3 sets of data, keeping the same indexing, so that if row number 1 in one set corresponds to row number 1, 2, second, and third. And
Yeah, so what I will do is I would split my, so if let's say X is my, so say if I have input, okay, let's go, okay, I can write here, right? So say, if X is my, let's say data, and, X has a shape of, let's do it right in here, right? So X has a shape of 1000, because 1000 is the number of unique examples, and 33, where 33 is all the different features, but let's say it's 11, 11, 11. So I will separate this to X1, which is basically 1000 into 11, and then X2, which is 1000 into 11, so not 1000 by 11, then they have X3 and 1000 by 11. So now I will basically just use Keras like a functional model builder, and then I will have one dense layer here that feeds X1 here. I'll show you. So something like this, right? So basically you'll have, because typically you are used to just having one input layer in Keras, right? So you can, but you can have multiple input layer. You can connect any part of the Keras you can, you can connect. So you can just have, one input layer. You can call it input 1. This, this is connected to input 2. This is connected to input 3. And now you have, dense 1, which is connected here. Dense 2. Dense 3. So I could scroll. There's really no scrolling here. So now I will basically concatenate dense 1, dense 2, dense 3 by using Keras. So if you do like this, right? So concatenate and X comma Y. So you basically do X1, comma X2, comma X3. So when you concatenate, so it will look like this, right? So basically you'll have this kind of thing. So if you actually do the Keras plot, which I showed you in the second week, you'll basically see like this. So you have a concatenation of this, and then from here onwards, you have just one layer, and then you continue. So this is how you have, let's say, now let's call this as a dense combined 1, and then you will have another dense combined 1. So combined 2. And then, you have a softmax. That's it. So this is what your architecture would look like.
Thank you. All right. I'll let somebody else ask a question now.
Sure.
So, we've talked about a kind of variety of different image classification tasks. And one of the things I was wondering is how much in like state-of-the-art networks are different types of like signal processing used. Like for instance, it's been a while since I took my signals class back in undergrad, but like a bandpass filter or something like that. It seems like something like that would maybe be helpful, or like in video classification, a particle filter for tracking an object, right? Like an object probably can't move from, it can only move so fast, right? It's not going to teleport, across the screen. So there's a limit to what it could realistically do.
Yeah. So what you're asking is what, for a long time people, so initially when people started getting popular, people were still, trying to put their handcrafted features. What, all these signal processing techniques are basically your handcrafted ideas, right? So people used to do that initially, but at least in the last few years, it has kind of become concrete that the less things you add, because so these are called as, priors, right? These are called as your inductive biases. So the less inductive bias you add, better because although it doesn't make us feel good, because we as a human, we like to think, oh, you know what, oh, I know some signal processing, maybe I can add this type of that type of filter. But in the end, all of those underperform directly learning from the raw data. So the rawest form of the data, so if you have a signal or video directly giving raw pixel values, raw input values, and then just letting the kernels or letting the filter, the networks learn whatever they want, is actually better, because they really learn the filter that are optimized for this task. But of course, the problem is those things might not always generalize, or you might not have enough confidence because they might be doing something funky. So if you really believe in your signal processing techniques, filtering techniques, you should add them. Definitely it's easy to add them as one of the input, one of the intermediate layers. But general understanding in the field of deep learning is don't give the human input, let the model learn, and it turns out it learns really well and learns with that. So practically speaking, you don't have to add any signal processing stuff to it. So this, I hope you'll keep this diagram in mind, where in classical machine learning, you have the input, you hand design the features, extract the feature values. But with deep learning, input and all of this in gray are was learned. Let the network learn what it wants to learn. If you have enough data, it will learn the most useful feature that you had not even thought of.
Okay. Yeah. Based on my other question, yeah, it really is about just staying out of the way, I guess.
I mean, and for a long time, people didn't like that, right? Because people would like to think that we are much smarter than machine and we can tell the network what features to use. But it turns out data is very complicated, and the less you tell it, the less restrictions you add, the better it is able to learn.
Okay. Thanks.
Any other questions? Okay, if no more questions, I will grade your assignment 1 to your tomorrow. I'll send you the notes. I'll try to grade assignment 2 as soon as deadline is over, and I will, the final project grading, probably you will not, you'll see the project grade along with the final course grade because there's not much time between them. But again, just because course has ended, it doesn't mean anything. I will keep the Slack open. You guys can continue using that. Feel free to reach out to me. Feel free to share some code or some paper that you came across or some idea. And I hope you guys will continue to learn, because definitely this is only the start. Like there's so much more in this field. But at some point, once you've learned a lot of different topics, in the long run, I would encourage you to pick certain areas and really go deeper in them and specialize in them, rather than, because there's no place for really a jack of all trade, because it's so complicated, so advanced that if you really want to, let's say, work in healthcare, you have to really specialize in these kind of ML type techniques. If you really want to work on image processing, specialize in CNNs. If you really want to work on text, specialize on this GPT and image embedding models. It's good to understand a little bit more, but in the long run, you'll be best suited by forgetting about all the other stuff and just really going deep in certain areas and really becoming master at it. And like for example, one website which I love is called as paperswithcode.com, where because not every paper has a code. So here you'll be able to find your nice papers which actually have code so that you can play with it. And they also have benchmarks. They have all the data sets, methods. So it's really useful. So I would definitely encourage you to use this website to learn more, find things, and you'll say you want to learn. And of course, Hugging Face is also really good, right? Because people upload their models. So if you don't have compute space, you don't have to compute yourself. You can just use other people's model. And I've already showed you how to use them, right? So you can see performance. There are people, there's a community and people, chat about it. If there's an issue, somebody will fix it. So I think, because this field is still advancing, and to be honest, I cannot tell you what will be, the technique that will rule in the next 4 or 5 years, because GAN came, people were making fun of it. Then suddenly GANs became so good that people thought GANs will be the end all. Then now you have diffusion, and now even diffusion is being replaced. So who knows in 3 years what will be the state of the art. But as long as you understand the fundamentals, you will be able to read the papers, or read the blog post, and be able to understand what's going on. Like the other really good websites called as distill.pub, where they do write in a blog, or it's like in between scientific paper and a blog where it's very interactive. Actually, I was trying to add a lot of GNN for today's lecture, but I thought there's already too much content. But here, it's very interactive. You can, read this and play with the data, play with the things, and you can, get a good sense of, how things are built. So I'll definitely encourage you to, keep these things in your radar, and whenever there's a new post, try to read them, because this is really, well, they put a lot of effort into, making these things. Yeah. Other than that, I hope it was, useful, and please don't hesitate to reach out to me if you need any more help with the project or with the, with reading the material.
All right. Well, thank you.